right. Our last speaker for today is going to be Gaétan Borot, and he'll tell us about Chern-Simons theory on S3 mod G and topological strings.
It's better? Yes. Okay. Okay. So there's a long history of works in physics and in mathematics to relate Chern-Simons theory and topological strings. So to reiterate a bit the problem, I just want to briefly summarize. So if you look at UN Chern-Simons theory on S3 at level K, this Witten had shown that this is dual to topological strings. On the cotangent, actually it's true for any 3 manifold, so there was supposed to be an M here. Where you have n Lagrangian branes, so that's the rank of the gauge group, wrapping the 0 section. And if you go one step further, one ingredient was added by Kumar and Vafa, that's said by geometric transitions. This is also dual to some closed topological strings on threefold, where you just squeeze the S3 and then resolve. And what you obtain is a resolved conifold. So mathematically, that means that there is identification between the Chern-Simons partition function on S3 and the Gromov-Witten invariance of the resolved conifold. And so this can be checked explicitly in the closed sectors. And this was generalized also to the open sector by Oguri and Vafa. So they construct some Lagrangian here so that the Wilson lines of the unknot in this Chern-Simons theory on S3 will encode open Gromov-Witten invariance of this resolved conifold. And this has been mathematically proved since then. So I'm interested in generalizing that to other manifolds, so simple manifolds. So for cyclic quotient of S3, this is already pretty clear. So here, you can take the ZP quotient of the resolved conifold. This is still a toric threefold, three orbifold. And here on the Chern-Simons side, you also have a matrix model representation for this Chern-Simons partition function due to Marcos Marinho, and you can compute what's the spectral curve of this matrix model. And by general results, we know that the large N expansion of this matrix model is given by the topological recursion of NR and Orentin on the spectral curve of the matrix model. So that's this side. On the other hand, you can again do geometric transitions, and here. This is toric, so in principle you have toric mirror symmetry, and you can check that the mirror curve of this is indeed the spectral curve of the matrix model. Besides, for toric Calabi-Yau, we have now, it's mathematically proved, this BK-MP conjecture, so topological recursion on the mirror curve for toric Calabi-Yau should compute open Gromov-Witten invariance. So these two things coincide. So what I want to say today is what happens when you do non-abelian quotient of S3. So here, I have 2 messages for this talk. The first one is that, okay, there's a matrix model here, again due to Marinho, which computes this partition function. You can study this matrix model, compute the spectral curve, large N expansions given by topological recursion. First message, the spectral curve coincides with the specialization of the spectral curve of relativistic Toda of type ADE, where the ADE depends on which group you are dividing by. The second message is on the string side. So the first one is a mathematical statement. The second one is more physical and in some sense explains why this identification of spectral curves. So once you're here, there's the F0 here is also the prepotential by geometric engineering, for a 5D gauge theory with gauge group ADE. Again, I will say it's related to gamma. And then you can use this gauge integrable system correspondence developed by Nekrasov, which said that this, at least in the A case, but you can easily generalize to the D and E case. And here, that should be governed by a Seibach-Witten curve that should be the spectral curve of relativistic Toda. So that was natural to propose that this should match, and that's essentially what we proved. Okay. So on the Chern-Simons side. So actually, the Chern-Simons partition function can be written quite explicitly for a larger class on theoretical, which is called ciphered spaces. So you can think in two ways, either as three-manifold obtained by rational surgery on this very simple link, or as S1 bundle over orbifold S2. So there are orbifold points, and there are important parameters defining this geometry. So the most important one are these A1, AR, which are the orders of the exceptional fibers in this representation. So the orbifold Euler characteristics of the orbifold S2 it plays quite an important role. If this is positive, then the three-manifold is a finite quotient of S3. And actually, you exhaust all possibility in this way. So if you just look in here, you have just integers, R integers, and you want to specify all cases for which this is positive. It's a very simple problem. You find a list, which is here. So either you have 2 exceptional fibers or 3 with those cases. And it corresponds actually to the ADE classification of subgroups of isometries of S3. So the reason for that is that S3, you can think of it as SU2. So you can act on the left and on the right by multiplication, by a SU2 matrix. So then up to central extension, finite subgroup of isometries of S3 are just given by finite subgroup of SU2. And this has an ADE classification where Mach-K correspondence comes into play. So this corresponds to those cases. When you take 2 exceptional fibers, you realize length spaces. It corresponds to the A series. And the other case, so all those groups as subgroup of SU2, they are called the binary polyhedral groups. And for us, the most interesting, I would say, is when you realize the Poincare sphere, which is when you divide S3 by the binary icosahedral group of order 120. And this is the only integer homology sphere with finite pi 1, which is not S3. Okay, so it's this type of manifold I will focus on. So as I said, because these manifolds are very simply presented in either of these two ways, it's one of the special cases where you can actually compute Chern-Simons partition function in some way. So strictly speaking, I will be dealing with the LMO invariant. So this is a graph-valued invariant you can attach to a three-manifold, which essentially is the sum of Feynman graphs of Chern-Simons theory. And if you choose a gauge group, so here SUN, this Feynman graph, you give a value to each of them. So you obtain a formal series valued invariant. So it's a formal series in H bar, where there should be, I guess, a 2G minus 2 here. And in the power U, which was n times H bar for me. N is the rank, H bar the coupling constant. Right. So this is defined for any rational homology sphere. And by surgery formula Banatan and Lorentz, this can be written as a matrix model with a Gaussian potential and this funny interaction here. You can start really from Chern-Simons and first principle in Chern-Simons and also compute what is the full Chern-Simons partition function. That's actually what Marino did even before that formula was existing. And you obtain something like that plus residual term corresponding to irreducible flat connections. And this formula has been re-derived by various methods, either using, so Marino used the surgery representation, these people rather used the orbifold presentation and counted bundles here. Right, so I will focus on LMO, which is just one term of this partition function. And in the case of the Poincare sphere, the trivial flat connection is related. And this indeed corresponds to the contribution to that of the trivial flat connection. Right. Okay. So this is for the partition function. But if you want to insert Wilson lines along very special knots, which are the one going along the fibers, the exceptional fibers over here, they're represented as taking expectation value in this matrix model. So what we want to do is to compute in a large N expansion the partition function here, and also all correlation functions. Right. So I have this and this trace over Zollman, which is just another way to encode the partition, so the correlators, so all the Wilson lines for any representations. And I would like to know how they behave when N goes to infinity, and can I compute these expansion? So here there are two general results, which is based on some audio works I did with various people. So first, if this orbifold characteristic is positive, so in the case of S3 mod a finite group, then at least for a small value of U, which is n times n bar of the good sign, there exists an asymptotic expansion for these quantities. So the LMO is a priori defined only as a formal series in H bar and U. But once you have this formula, that makes sense for any n integer and u positive of the good sign. So then the statement, the non-trivial statement here, it's an asymptotic expansion. And that thing allows you by, then you have this fg, which is a function of u, and you can try to study analytic continuation of that. Right. So these coefficients exist. The second theorem is that they are computed by the topological recursion of Hénard and Orentin applied to the spectral curve of the matrix model. And actually, topological recursion take another piece of initial data, which is the leading covariance of the matrix model. So basically, if you have computed this, there's a universal algorithm that computes for you the higher omega gn and fg. In particular, the singularities in the u plane of these quantities, so of the resummation of LMO invariance, can be just deduced from the behavior of this family of spectral curves depending on u. Where are the singularity in the complex plane here? So what remains to do is to compute the spectral curve. So this is something that we did in the first work with Hénard. So in a matrix model, when you want to compute the spectral curve, it's characterized by a Riemann-Hilbert problem. So here's the one you get for this Chern-Simons matrix model. So you have this large n limit of the resolvent. You take the exponential with some coefficient. And then you know that this has some discontinuity in the complex plane, so which is here. And the Riemann-Hilbert problem tells you that the value of the function just below and just above is related to the value of the function elsewhere, and elsewhere is at rotations here on the complex plane. So it's a non-local problem. It's not obvious to solve that. You can reformulate that by saying, okay, I take a vector in z to the a. So a is the number of cuts here, the angle of rotation. And I just take the rotation of this function y to the power of vj, which is the jth component of this vector. And these equations translate into an equation for this. So now this, because we put, so initially this y had a cut here. When we make rotations, we'll have cuts here, here, and here. So this may have cut everywhere on all these rotated cuts. And this equation translates into the fact that there is some linear involution, Sj, which is a pseudo reflection, so in a dimension, so that the value of this big y of v at x plus I0 on the jth cut is the y of Sj of v at just below the cut. So using that, you can perform analytic continuation. So you have a function defined over here. Initially, you choose an initial v. And you say that I can analytically continue that to another sheet by y Sj v of x. And then there might be other cuts. So we'll continue the process. So in that way, you define a Riemann surface on which that thing will be analytically continued, and that's the spectral curve. However, there's bad news, which is in general the group generated by this Sj that you have to understand to know the topology of the spectral curve is infinite. So what's more relevant is actually to say, does it have any vector non-zero with finite orbit? Because then I can take such a vector, and the y of v will be an algebraic function of x. In that case, you can find a polynomial relation, and that you can try to compute just by knowing the ramification data of your spectral curve, knowing the growth conditions that are provided initially. So that's the favorable case. So here's the result. If chi is negative, is equal to 0 or positive, if and only if there exists a vector of finite orbit. So only in those cases you can expect to have an algebraic spectral curve. So then, in those cases, if you just focus on chi positive, take all vectors which have a finite orbit. So then the restriction of that big group will be finite. And what we prove, check case by case, it's a Weil group. So here are all the cases. So I didn't put the A because it's more or less standard, already done in literature. But you get something here. So that's how I classify my finite subgroup of SU2. And here you get a monodromy group, which is finite, which is of this type, which in general differ from this one. It looks to be smaller. So that will be explained later. And for the Poincare sphere, well, you do get here the E8 Weil group. So you get a curve of degree 240 in Y, 18 in capital X, which is here small x to the 30. And I should say E8 is the only case where we could not complete the computation. Probably it will take more than 100 lifetime to do that. However, in all the other cases, here we have the complete answer for the spectral curve. So it's a function of a parameter u, so we have all the coefficients. And here we have this polynomial up to 2 parameters that are fixed in terms of u by huge algebraic constraints that we cannot solve really explicitly. Okay. So that's on the matrix model side. Now, the second thing I want to say is that we can identify that curve with a specialization of the spectral curve of Toda. So I should explain what that means. So here, you take any simple Lie algebra, complex simple Lie algebra, and you will define what's called an integrable system related to that, which is called relativistic Toda. So you take a Chevalier generators for this G, and exponentiate them with some parameter psi, so 1 for each node in the Dynkin diagram. Make this ordered product, and here actually you add the affine nodes to G and add some dependence in X, which is a spectral parameter. So this is an element in the exponential of G. And these parameters here, you will define a Poisson structure on them. So I should say that this integrable system in the exceptional case of D and E has been defined by Fock and Mashakov and independently by Williams, Harold Williams, who is here. So you take this Poisson structure, so this is the exchange matrix of the quiver, which is the doubling of the affine quiver of the Lie algebra. And I didn't put the arrows here, but there's a natural way to put the arrows. And this, because you were in the affine case, this has a Casimirs. So here the Li's are the coefficients of the longest root in the fundamental basis. Right. So you have a Casimir, so this will remain as a parameter. Then this Lex matrix, if you just take the trace in the fundamental representations of the Lie algebra, that will provide a complete set of Hamiltonians in involution. That's what these people checked. Right. So now, what I mean by spectral curve of this integrable system is, actually, we'll take a very specific one. I will take a representation of minimal dimension. That's the simplest thing you can think of. And I will compute the characteristic polynomial of this in this representation rho. So since L depends on X, that will be a polynomial in X and Y. And also, all the other traces or exterior powers of rho of L can be expressed in terms of these Hamiltonians. So it's actually a function of T0, etc., up to TR. T0 being related to this Casimir. So that has a definition, and in principle, you can try to compute it. It takes some time. However, here's the result we arrived to. So I say that this is my K correspondent associated to U. For a finite subgroup as U2, you have it's attached to that a Dynkin diagram. And then you can consider a simple Lie algebra associated to that Dynkin diagram. And then, if you part T0 of U, which is this exponential, then there exist some functions, which are actually algebraic functions of T0 of U, so that the LMO spectral curve will coincide up to some power here with the Toda restriction of Toda spectral curve. So we have proved that for all cases except E8. Unfortunately, this one resists a bit computation. And I have to say that I have to explain a bit what's this. I mean, here, this curve in general has Weil symmetry, Weil ADE, whereas what we see for the matrix model spectral curve is something smaller. And this is due to some symmetric breaking. Essentially, since you're taking the teeth to be in some very specific one-dimensional slice, this imposes some extra factorization property for this, and this explains the symmetry breaking in all the cases, which except E8, where it's the same. So that we have checked quite. I mean, we could explain that really by computing. Okay. So here's the example for the E8. What we can do in that case is to say what's the Newton polygon and what are all the coefficients on the boundary. But of course, all the thing in the middle, we don't know. It's still, this curve is as a plane curve, it's quite singular. So also there are a lot of interior points. The genus is only 1,471. So it's quite small for a curve of that degree. The other check we can do on both sides is that for U equals 0, so it's n times h bar, but h bar goes to 0 very quick, we have this, which is just actually the product of all the slope polynomials, and that agree on both sides. So it's a non-trivial check that supports this conjecture for E8. Right. So the reason to propose that, first, why we thought that this could be related to Toda, so come from physics. So as I said, you have geometric transitions. So if you take the cotangent of S3 as a fiber of one of this, and then you just squeeze the S3 and then resolve, you get the resolved conifold. So you can take the gamma quotient of this, you get a Calabi-Yau orbifold, so it's above P1, where the fibers are these simple singularities of surfaces, C2 mod gamma. However, this thing is non-toric, because these extra generators we have in the group gamma break some of the torus action. Only one is remaining. Okay. And once you have this, you can also resolve fiber-wise this simple singularity of the surfaces. And then you get R plus 1 Kähler parameters, one for the base here, and the other for the exceptional P1s. And here the Mackey correspondence actually tells you what's the intersection of these P1s. It corresponds to the Cartan matrix of this Dynkin diagram. Okay, that's where you start to see appearing this the algebra. So following ideas of geometric engineering, actually, topological strengths on this should be related to gauge theory with this gauge group exponential of G gamma. And then that suggests that the mirror of this, also it's non-toric, should be given by this Seiberg-Witten curve. And for the A series, we know very well that this is the spectral curve relativistic Toda type A. So we just say that this should be the same for the D and E case. Right. So we can formulate this generalized Gopakkuma-Vafa conjecture, which is saying that these LMO genus G invariants correspond to the class sector of topological strings on this resolved gamma quotient of the conifold. If you specialize to the Kähler parameters, some very special one-dimensional slice. And also in an example, we have expressions for those. We don't know, so it looks like a kind of mirror map between the Chern parameter of Chern-Simons, which is n times h bar, and these Kähler parameters. However, it's quite very non-trivial and complicated. We don't know how to predict that from string theory. The thing that we can predict is what happens for u goes to 0 that corresponds to the orbifold regime here. So don't resolve the fibers. And then these values that we get here, so in the previous theorem, agrees with predictions from Krepin resolution conjecture. Okay. And there are also natural candidates for Lagrangian branes in this geometry, which allows to formulate, at least to formulate mathematically a conjecture for the open sector, for some holomorphic discount on this Lagrangian, which should match with the Wilson lines of the fiber knots invariant on these quotients. Okay. So these results lead to, I would say, two questions. First, so we just matched the spectral curve. Maybe it's the sign that actually there is a quantum version of this spectral curve. So you can take a non-commutative determinants of this Lax matrix. That will be some difference operator. And the result that we have so far, if you were looking at this expectation value in the matrix model, so that will be a certain generating series of Wilson lines along these fiber knots. The spectral curve that you get here, just the differential in the spectral curve here, the Seiberg-Witten differential, just appears in leading order when h bar goes to 0 of this. So it's natural to propose that there should exist some observable in the matrix model, so some certain knot invariants, which are unrelated by such a difference operator. And first, one should have defined precisely that and see does it define a quantization of these Toda Hamiltonians. And second, it would be interesting, can we derive such a difference equation directly for something like that from the matrix model? Okay. The second thing is that I showed you some match for the Kähler parameters which are in this very special one-dimensional family. Because in some sense, we only chose a trivial flat connection in Chern-Simons. So one can wonder whether this Gopakkuma-Vafa conjecture, generalized one, can be extended for all Kähler parameters, what they correspond to. So here's a natural candidate because if you look at the flat connections on these gamma quotients, it's just the same thing as representation from gamma to un, mod un. And here again, for these gammas, you just draw the Dynkin diagram, and you have exactly as many irreducible representations as the nodes of the affine Dynkin diagram. So a flat connection here just a point, a couple of integers n0, etc., n1 up to nr, which sums up to n. And then if you rescale, you can define some ui. So we have r plus 1 parameters here. Before we just had 1, because we just had this term. So it suggests that the Cartan subalgebra of this G gamma should match with, there's also the affine thing, should match with the large limit of this. And then you could say that the contribution of the flat connection parameterized by a point in there should correspond to, let's say, should be given by topological recursion on this, and should also correspond to Gromov-Witten on this resolution of the resolved conifor with those with a scalar parameter, which should be functions of these U's. So the problem with that, I mean, parameter counting seems to work. First, I say that we don't know, even for just when you have that, how to predict what's the value of Ti of U0. So we don't have this mirror map, so we don't really understand it. Second, actually, we don't have an expression, a matrix model expression for the contribution of that flat connection of Chern-Simons. So here, there's a bit of a puzzle. I wouldn't know where to start to try to check something like that. OK. So I think this is all what I wanted to say, and thank you for your attention.
And on behalf of the organizers, I was asked to remind everybody that we have a dinner today, and that showing up at this Maison des Polytechniciens at 7 would be a good time to show up so we can all be ready for dinner.